So, today we will start with the force analysis of mechanisms. Okay. And one of the first things we are typically interested in, so even before we go into, in many applications we use linkages to obtain a mechanical advantage, meaning for, so as human beings our ability to apply forces is limited and we may want to multiply that, effort, and being able to do that is what is known as, using some device to do that is what is known as mechanical advantage. As you all know, using levers for instance, we do that. Now we are going to look at the mechanical advantage of mechanisms. So, usually you are using a mechanism to either transmit force or torque. You can also use, other than linkages, gear trains are another example where you can change the torque between the input and the output. One difference between a mechanism and a gear train is that a gear train will operate with a constant velocity ratio or torque ratio. Okay, you cannot, whereas in the case of a mechanism it varies as the mechanism moves, because this is dependent on the geometry of the linkage. Okay, so the torque ratio is a function of the speed or angular velocity ratio, which can be determined from the geometry, angular velocity ratio between the input and the output. You remember, even while doing the velocity analysis, many times we are only interested between what is the output. You may not be interested in the intermediate links so much, say angular velocity of the intermediate links. One reason is because you are usually interested in the torque ratio between the input and the output. Okay. So, and this is a function of geometric parameters and varies as the linkage moves. So, typically we look at it as in terms of work or power. You say if this is your linkage black box, right, you have some power or energy input and you have some power or corresponding power or energy output that you are interested in. And if you assume there are no losses, in real life typically there will be losses due to, say, friction for instance, or inertial effects, but if you assume that there are no losses, then you say that the input power is equal to the output power. Whatever you put in, you are able to get out. Okay. So, typically we assume, when you say no losses, we assume they are negligible. compared to the power that you are transmitting. So, in the case of planar mechanisms, you can write this as P in can be written as the input torque times the angular velocity. It's typically T dot omega, right. The power is T dot omega or F dot V, the dot product of these two vectors. In the planar case, both T and omega will be along the, you can about the same axis. And so, you can write this as this is equal to plus or minus T out omega out. Or you could also have F out dot V out. So, if it is a slider crank, for example. Okay. So, this is exerted on the linkage, the output power is exerted by the linkage. So, you do not need the plus minus sign if it is understood that this is on the linkage and that is by the linkage. So, if you have F dot V, this is just Fx Bx plus Fy Vy, where V is the velocity of the point at which F acts. Okay. So, if you have omega in, some omega out, and you have some input torque, let us say the output torque is this. Okay, it's say there is a load that is being lifted, load that is attached to this link. So, it is the resistance is your output torque. Okay. So, if you have something connected to this which is lifting a load, okay, so the resistance. So, then you have T in omega in equal to omega out. Depending on the directions you would use, if both are in the same direction it will be plus, otherwise minus. So, T out by T in is omega in by omega out. And your mechanical advantage is defined as, the standard definition is F out by F in, okay, because usually the torque also may be applied as a force at a distance. So, this could be R in, okay. So, T in will be F in R in, vectorial form R cross F, but here assuming this is perpendicular to this, say F in R. The standard sometimes in the case of linkages it may also be defined as T out by T in, if you are interested in the torque itself, okay. So, where say you are applying it through a motor, then rather than talking about a force applied at a certain distance, you would talk about the torque itself. So, MA would be if T out meaning F out, sorry, T out by R out by T in by R in, which is T in. And this is equal to, from this you have, this is equal to this by omega in by omega out. So, this is the ratio of distances at which the forces are applied. And this here is my angular velocity ratio, which depends on the geometry of the linkage. Yes?
For a crank rock, you don't apply a force, but always give a torque of.
Yeah.
So
So, you could define it as F out by torque. So, then you would,
the definition
yeah, the definition would be different, because there you are resisting a force, you are talking about a slider crank.
crank rock,
Crank rocker, yeah, you can, so you can define it there as T out by T in. Okay. The general definition of mechanical advantage is F out by F in, because in that case you can just treat it as, you have a constant, because R in and R out, if they do not change, you can say that this is, you can define it in terms of the input and output torques. So, this is, it depends on the geometry, mainly the ICs. You can, from an instant center analysis, I can find the ratio of omega in by omega out. Okay. So, let us look at let us say I have a punch, say this is a sheet of metal into which I want to punch a hole. Okay. So, this is the handle, so I would be applying a force there in order to punch a hole through this sheet. So, I may have a table that has, on which the sheet is placed, and then it will punch the hole. Okay. Okay. So, now this would be the input force I am applying at a distance R in. Okay, this is essentially a 4 bar linkage. I have 1, 2, 3, 4. And the output force will be what is being applied here, and that is being applied at a distance r out. So, this is f out actually. Okay. The punch is going to apply that force on the sheet, that is f out acting at a distance r out. Okay. So, now what would be f out? So, given say the geometry of this linkage, what would be out f out and the mechanical advantage of this linkage, okay, given some dimensions. Okay, let us say we neglect the weight of the links, because otherwise there will be losses due to the inertia of the links themselves. So, we are assuming that there are no kinds of losses in this system. So, I have f out by f in, that is my mechanical advantage, that is equal to, I showed you that that is equal to omega in by omega out into r in by r out. Okay. Now, what is omega in by omega out? How can I find that? Any ideas? I can do a velocity analysis, or I can just find the instant centers, right. I can find the instant centers. So, here 2 is my input. So, I want, in this case this is omega 2 by omega 4 r in by r out. Okay. So, omega 2 by omega 4, which means I need to find the instant center I 24, I 12, I 14 and I 24 are the instant centers I need. So, this is I 12, I 14 and this is I 23, I 34. So, this point here is I 24. So, what is omega 2 by omega 4? Right. So, what here I know that the velocity of I 24 is the same whether I consider it as a point on body 2 or body 4. So, I have velocity of I 24 equals omega 2 into I 12 I 24, which is equal to omega 4 into I 14 I 24, right. So, omega 2 by omega 4 is I 14 I 24 by I 12 I 24 into R in by R out. Okay. And in this case this is positive because I 24 lies outside the line joining I 14 and I 12. Okay. So, this is so now if I look here, my F out is F in times this quantity I14, I24 by I12, I24 R in by R out. You can see this is going to be greater than 1. Okay, you can see this ratio is greater than 1. So is this ratio. Okay, so my F out is necessarily a multiple, is multiplied. So you can take, so here if I just look at these distances, this is about what, 6 times the other distance, just some, I could take that based on what I have here, and then R in by R out about 4 times. Okay. So my input force is multiplied by 24 times. Okay. Typically an operator may be able to apply like somewhere between 5 to 10 kgs up to 100 Newton. That can be multiplied 24 times. Okay, using this linkage. If you were just trying to do without the linkage, you wouldn't get this kind of a magnification. So this, and again if I wanted a greater mechanical advantage, I have control over, because this is all based on geometry, right? All of these can be, I can play with these parameters. Of course, it is not going to be the same at every point in the during the motion of the linkage, okay, because the instant center changes as. So here you see that as this moves, I23 moves closer to the line joining I12, you get this becomes smaller and smaller, and you get a high mechanical advantage, right. In some other position where I23, where I24 may be here, okay, your mechanical advantage would not be high, right. So as you are nearing the toggle position, you find that where these two links are will be in line, and in that case I24 and I12 will actually coincide, right, which makes the mechanical advantage infinite, but obviously you cannot, the parts have to be able to withstand the forces. So, but close to the toggle position you can see that you can get a really high mechanical advantage. So, most punch presses or anything that is where you want to generate, they will operate close to the toggle position. Okay. So, you look at how you, and then of course it is intuitive that R in should be much larger than R out. So, if I increase that input lever, okay, then I can increase this ratio as well. Okay. So, it can be a good design tool when you are in the, because this is all dependent on geometry. So, I can look at how I can modify these parameters so that I get a good, even clamps, when you want to clamp something, you want a high force to hold something in, this kind of a mechanism is used, and it operates near the toggle position. If you look at brakes in wheelchairs, you will find that it will have a 4-bar mechanism, it will be close to the toggle position, it will operate close to the toggle position. Okay. Clamps in the workshop or punch presses all operate based on this. Okay. So, I will show you a real life example. So, this is a wheelchair, this is a mechanism for a wheelchair that operates like a regular wheelchair, but it can allow the user to come up to the standing position. So, many wheelchair users, they cannot stand on their own, okay, because they do not have the required muscle strength to stand up on their own. So, they need something to support the lower, especially at the knee, okay. But lifting themselves, so for them, but it's standing is very essential, because if you are in the seated position all the time, I mean even as able bodied people, we are encouraged to get up and walk around every hour or so, right. They say do not sit in one place for a long time, because it is not good for your health, it affects the physiology, it affects in the case of a person who has, say, a spinal cord injury and who can't stand and is sitting in the wheelchair all day long, they may come up with other secondary health problems also, okay. Their circulation gets affected, their bone density starts going down because their legs are not weight bearing at all. So, standing as therapy is considered very essential for people who have to use a wheelchair all the time, but it is also very difficult, because at least two people have to lift them up. You have to lift up the entire body weight in order to make a person stand, and then support it, because their legs can't. So, this is basically just a mechanism that is integrated into the wheelchair, so that it is like this. If you ask somebody to exercise, okay, you may do it, may not do it. You tell somebody, okay, know what, just take the stair, you do not have to do anything special, but do not take the lift, just start climbing stairs, just start parking far away, walk. You are more likely to integrate it into your daily life. The idea is, if it is part of the wheelchair, then they will use the standing feature more often. What is special about this design is it is completely mechanical. There is no motor here. They are using only their upper arm power to essentially lift themselves up to the standing position. And the other aspect that comes into is, so if you look at the linkage, so this is the kinematic diagram of the linkage. So, here you see we use a parallelogram mechanism for the standing, because you want the backrest to always remain straight as the person goes to the standing position. Okay, you can see as he is moving up or down, the inclination of the back remains the same. So, the easiest way to do that is to use a parallelogram mechanism, but the mechanism that we are really interested in here is this one. Okay. This is the 4 bar, just a 4 bar. Okay. So, the other part is just a parallelogram. So, let us just ignore that for now. This is the mechanism that I am using with the handle to actuate. Okay. So, this is just a coupler point on this link EF, where I have to make it so that it is accessible to the person. So, if I look at this, then the person is going to be applying some force here to actuate the mechanism. What you are trying to lift is what is the external load? The weight. Okay. Let us say even we ignore the weight of the links and all that, the weight of the person is acting on that seat. Okay. So, there has to be the input torque has to overcome the torque due to the weight about this point. So, this is if this is my 4 bar, this is 1, 2, 3, 4, then this point here is, what is that point? This point here is I13, where those two links intersect. Okay. This point here is I14. Okay. Link 3, I can consider it as rotation about this fixed pivot I13, the motion of link 3. So, the torque that is being applied, the input torque is F in times the distance. So, say this point is H, the distance from H to I13, that is the input torque that I can apply. The weight, the output torque that has to be overcome is W times, let us say this is cos theta, okay, and let us say this is acting at a point P on that link, P I14 cos theta. It is going to vary, but imagine at theta equal to 0 to start lifting, okay, that is a pretty huge task to lift this weight. This is the torque you have to overcome. Okay. So, you know, how long can you make this handle? So, the longer the handle, obviously you will have, you know, to even get any mechanical advantage you have to have, because the amount of force that you are able to apply with your hands is going to be a lot lower than the W. Okay. So, this is actually not possible. It is only possible because of an additional link here. So, here I would have to apply a pretty high force. Okay. If you look at the dimensions, I can't make this too high, the H can't be, no, I can't try to, because ergonomically then I won't be able to push. I will be able to apply the maximum force at some optimum height. Okay. Beyond that, if the handle is here, the force that I am able to generate because of the way my body is structured, I am not going to be able to apply the maximum force. So, then what do we do? So, that is where, so if you just had the mechanism, kinematically yes, you can generate, you know, you can make it move. Okay. Kinematically I can simulate it, but if I put a weight on it, okay, I cannot apply enough force to make it come up to the standing position. Yes.
In addition to that, ma'am, in the video, irrespective of how much ever the person lifted, the mechanism blocked there, and this happened while going up as well as going down. So, does that imply there is a worm gear that has been put in?
No, no. So, there in the locking mechanism is by ensuring that in the sitting position it is at a toggle position, the standing position also you come to a toggle position, and then you have a positive lock, but the toggle position is what is locking the mechanism. So, the linkage dimensions are chosen such that it toggles at the sitting position and toggles at the full standing position, so that you do not go beyond that. So, that Yes. Sorry? Do I have a simulation of the kinematic diagram? No. Hmm? What are the rigid points? These are, so these are the fixed pivots. E, D, no, D is not a fixed pivot, D is the backrest. D is the backrest of the, but this link, this is welded here. So, it maintains the same orientation, it is part of this parallelogram linkage ABCD, okay, and because it is a parallelogram linkage, as this linkage moves, this orientation does not change, and that is the backrest. So, this just shows that the backrest is rigidly attached to this link, but these are part of the frame of the wheelchair. So, what I was coming to was, with just, so this is my parallelogram linkage to maintain the backrest vertical, and to that I am adding a driver diode EF FG, because this is essentially 2 more links. So, this is now a 6 bar that I have, okay, to actuate. The driver diode is to actuate the mechanism, not necessarily full 360 degrees, but that is my actuation for the parallelogram linkage. But because the weight is pretty high, unless I have like a really long lever, I am not really going to get much of a mechanical advantage. So, it is going to be that is where this spring comes in. So, this is essentially a gas spring. So, it is like you have a piston moving inside a cylinder, and there is a force that it exerts at every point. So, now what happens is, I have this linkage, this 4 bar, okay. This is I13, I14, and say, no, shouldn't do that. This is W, and this is F in. So, the person is pushing the lever like that. Yes, Abhijit.
Is it valid to call EFG as a driver diode? Because
Why are you saying it is not giving the input? My input is through EF.
through H, right? So
But H is a point on link EF.
yeah, but usually for the driver diode itself.
So, driver diode meaning that is, it is an additional 2 links. Diode means 2 links through which you are actuating the mechanism. So, here I am not actuating through say link FG, I am instead actuating through link EF, and H is a point on link EF. Okay. So, do not get caught up on the terminology aspect of it. It is still 2 additional links through which the original 4 bar, which is the parallelogram mechanism, is being actuated. Okay. So, it is, we can still call this a driver diode. So, you have F in into, call this point H, let us say we call this point P here, where the into H I13 is equal to W into P I14 cos theta, okay, in which case Fn has to be very high to do that. and that may not be possible. And that is where we use this gas spring that now applies an additional force Fg on this linkage, which helps to balance the weight. Okay. So, I have Fg, I am taking this as perpendicular here, but that would act at some angle. Suppose say at that particular instant it is perpendicular, then I have F in Hi13 will be equal to W Pi14 cos theta minus Fg into, say this point is G into I14. So, you can get compact gas springs which can apply pretty high forces. So, what that does is it reduces the input torque that I have to apply. This is sort of the idea behind spring balancing also.
Force is constant.
So, that will also vary as the length changes. There will be a constant force plus a force due to like a regular spring, right. In a regular spring you have F equal to Kx. Here you will have a constant force plus K times the displacement. Okay. You could use the first design that we used a compression spring or an extension, one of the two. We used an extension spring or the problem with that is when the person goes up, right, it just jumps because there is no damping present in that. So, a gas spring is better because of its damping characteristics. So, it is gradual, it does not just throw the person up like that. Okay. So, use of this can reduce the input torque that you require. So, it is not just about the mechanical advantage, but also about reducing the input torque required, and this is sort of what. So, we will look at spring balancing in one class, but balancing in general and then specifically, but this is a good example where spring balancing has helped you reduce the input torque. Okay.